This video will give an introduction to integration by parts. Now, from a big picture perspective, much like a U substitution undoes the chain rule of differentiation, integration by parts is going to be a technique of integration that undoes the product rule of differentiation. So to begin, let's just recall that product rule of differentiation. It tells us if we differentiate this product, f times g, we get the derivative of the first times the second plus the first times the derivative of the second. And now that we have this product rule written out, what I would like to do is just integrate or anti-differentiate each term. And keep in mind that when you anti-differentiate a derivative, you just get that function back. So the antiderivative on the left would be f of x times g of x. And on the right, we would get the antiderivative, and I'm just going to change the order of multiplication. I'm going to write this as g of x times f prime x plus the antiderivative of f of x times g prime x. And if we were to maybe isolate what we have on the right-hand side there, this integral of f times g prime, this will be equal to the f of x, g of x, which is already on the left, and then subtract away the integral of g of x, f prime x, dx. And the formula that we see here is what we will think of as being integration by parts. So the general formula for integration by parts is this first boxed equation, which is given here, exactly what we saw on the previous slide. But in terms of maybe remembering this and actually applying it to specific examples, it's easiest or maybe most convenient to do something like, say, let u be f of x and v be g of x. So that in this formula that we have f is u, g prime x dx is dv equals uv minus the integral of v du, which gives us this equation on the bottom. So the antiderivative of u dv is uv minus the integral of v du, which is in general just a convenient way to maybe remember the integration by parts formula, as well as a convenient thing when we're actually applying it to a specific example. So let's make a few key observations. So note in the form that we have above here, integration by parts is not actually solving the integral for us. What it's doing is taking a possibly complicated integral, what we start with, and expressing it in terms of what is hopefully going to be a simpler, easy to evaluate integral. Now, when we actually apply integration by parts and we start with this integral on the left, we have to have a choice of a function for u and a choice of a function for dv. And whatever we choose for dv, a rule here is that it has to be something that we can anti-differentiate, because in our formula we see that we have the integral of v du. So whatever we choose for dv is something we need to be able to anti-differentiate. Ideally, whatever we choose for u, the du is going to become a bit simpler. Now, when encountering a definite integral, this is very easy to take care of. All we do is take our formula and we just throw in those limits of integration on the right. In terms of when we would like to use integration by parts, so the most typical functions that we apply integration by parts to would be a polynomial, say x to a power times cosine or sine, a polynomial, so x to a power times an exponential times a sine or cosine, as well as inverse type functions, arcsine, arccosine, arctangent, natural log, etc. Additionally, depending upon how nice the function f of x is, it's also well suited to integrating things of the form x times f of x. And let's look at such an example. Let's evaluate the integral of x cosine x. And let me kind of start off here by just reminding us of this integration by parts formula. The integral of u dv equals uv minus the integral of v du. So looking at our integral, we need to pick something to be u and something to be dv. And many times, not always, but many times when we have something of this form, x times a function, x is a particularly nice choice for you. The reason being is that du is simply dx. It becomes simpler. But we do have to make sure that whatever function we pick to play the role of dv, it certainly needs to be something that we can integrate. So here dv is cosine x dx, so that v, its antiderivative, would be sine x. Now we go ahead and we apply integration by parts. So the integral of x cosine x is equal to, and how I remember this is I draw an arrow across the top row, so uv, so x sine x, and then I draw an arrow going downward from v to du. The fact that it's going backwards reminds me that I need a minus sign, so minus the integral of v du. So once again, integration by parts has not solved this integral for us, but what it has done is taken this original integral, which is maybe difficult to evaluate, and it has expressed it in terms of a much simpler, easy to evaluate integral for us. So the x sine x carries down. If we think of that minus sign as being inside the antiderivative, the integral of minus sine would be positive cosine plus constant of integration. And this shows a very simple yet typical application of integration by parts.